This is Chapter 6 from AS Applied Maths Statistics. We're now looking to introduce cumulative probabilities, so by the end of this section you should be able to calculate cumulative probabilities for the binomial distribution. 6.3 Cumulative Probabilities. The evaluation of binomial probabilities can be very tiresome, particularly when n is large. So for example, if we wanted to consider calculating the probability that x was less than or equal to 26 when x followed a binomial distribution where n was 50 and p was 0.6, if we were looking to use the probability mass function for the binomial distribution to do this, we would have to find the probability that x was equal to 0, and then add to that the probability that x was equal to 1, the probability that x was equal to 2, and so on, all the way up to the probability that x was equal to 26. So as you can imagine, this is just not realistic given how time consuming it could be. And for this reason, tables have been prepared to ease the burden for us, and you can also use your calculator to find probabilities, which we will touch on later in this video. So the tables that you will be provided with during your exam find the probabilities that x is less than or equal to a given value of x. It is really important to note that your tables and your calculators always represent less than or equal to when finding cumulative probabilities. So if you are asked for a given range or for a probability that x is greater than or equal to a particular value, we do just have to tweak the value we look up to make use of these cumulative probabilities, but we will touch on this in more detail later. Tables are given then to 4 decimal places, and your calculators will go slightly further than that. The cumulative probability function then for a random variable tells you the sum of all the individual probabilities up to and including a given value of x. So for example, if we wanted to look up the probability that x was less than or equal to 2, then the cumulative distribution tables would give us the sum of the probabilities for everything up to and including 2. So we would get the probability that x was equal to 0 plus the probability that x was equal to 1 and the probability that x was equal to 2. So considering an example, we're given that x follows a binomial distribution where n, so the number of trials, is 6, and our probability of success, p, is 0.35. We want to find the probability that x is less than or equal to 2. So to do this, we can use the binomial cumulative distribution tables. We need to find the section for when n is 6, which is just here. We're also given that the probability of success is 0.35, so we can go along this top row until we find 0.35. It is worth noting that not all the probabilities will be listed in these tables, and this is where your calculators will become really helpful. In this example, x is 2, so we've got 2. In terms of then reading off the probability, we need to just work across and down until we meet. So in this case, we meet at 0.6471. So we can just write down then our probability is equal to 0.6471. Please can everybody now pause the video and attempt example 6.3.1, looking up the following values using your tables. So hopefully everybody managed to attempt that example. Please find the answers below. If you've got any questions, please do get in touch with one of your teachers. As mentioned, you will be provided with tables during your exam to find cumulative probabilities for the binomial distribution, i.e. the probability that your random variable takes up to and including a given value of x. Your calculator can also be used to find binomial probabilities, and you will find that given the tables, not all values for p will be listed. You will just have certain ones in there. So that's when your calculator becomes really useful, because you can specifically define your variables for x, n and p. In particular, when considering the CASIO CLASSWIZ calculator, we would want to use the binomial CD function to find the probability that x was less than or equal to a given value of x, and the binomial PD function to find the probability that x was exactly equal to a given value. In terms of where these functions sit on your calculator, the first couple of steps are the same. So you would choose menu and then select 7 for distribution. From here we would specify whether we wanted the cumulative distribution or the probability distribution. So you would choose 4 for the probability distribution, and that's for if you was trying to find a single probability. So for example, if you wanted the probability that x was equal to 10, but you would press the arrow down once and then choose 1 for the binomial cumulative distribution if you wanted to find the sum of the probabilities up to and including a given value. So for example, if you wanted the probability that x was less than or equal to 10, from here you would select 2 for variable, and then you would go on to define your variables for x, n and p. Pressing equals would then present you with the associated probability. So if we look at the example that we've got here, so we're looking at the binomial PD, so it would say CD if I had pressed down and chosen 1 for binomial CD. Because we're looking at binomial PD, we know that I'm looking for the probability that x is exactly equal to a value, and my given value of x here is 10. So I'm trying to find the probability that x equals 10 when I've got a given binomial distribution where n is 25 and p is 0.37. So we're going to go on to a couple of examples now on the next slide. Please can you now pause the video and attempt to find the following probabilities using your calculator. So to quickly run through for this first example, because we're looking for the probability that x is exactly equal to a given value, we need binomial PD. N and P are given in our defined distribution, so we have n is equal to 8, P is equal to 0.25, and then we know that x is 3 in this case. So if you go ahead and put those into your calculator, you should have found that your probability is 0.2076. So then moving on to the two further examples then, in these ones we want the probability that x is less than or equal to a given value, so we should for these ones be thinking binomial CD, and we want CD because we want the cumulative, we want the sum of all those probabilities without us having to calculate each individual probability and add them together. If we use the cumulative distribution, it saves us lots of time. These two examples you actually looked up earlier using the tables, so you should find exactly the same values using your calculator, so you should be left with 0.6785 and 0.4402. Just a thought to leave with you for this first question. Although we can use binomial PD and it can sometimes be quicker to do that, if you were already in the binomial CD mode in your calculator, how could we use binomial CD to find the probability that x was exactly equal to a given value? Please can everybody now pause the video and look up the following using your calculator. So hopefully everybody has managed to find the following answers listed in the table. If you do have any questions, please do ask one of your teachers. Please just remember, when we are looking at the cumulative probability function for a random variable x, this does tell you the sum of all the individual probabilities up to and including, so just watch this equality sign here, that given value of x. So if we're looking at this final example, the probability that x is less than 7, we need to look up the probability that x is less than or equal to 6 if we want to use our cumulative probability function. Please can everybody pause the video and attempt example 6.3.3. So part A asks us to find the probability that x is equal to 5. So looking at our distribution that we've been given, we know that n is equal to 20 and p, our probability of success, is equal to 0.4. X then in this case is equal to 5, and that's if we're going to use binomial PD. Remember, binomial PD gives us the probability that x is exactly equal to a given value. So substituting those values into your calculator, you would get the final answer of 0.0746 straight away. So we could also use binomial CD. We just need to remember here that binomial CD does find the probability that x is less than or equal to a given value of x. So that does give us the sum of all the individual probabilities up to and including the given value of x in our calculation. So we want to find the probability that x is equal to 5, but we want to see if we can do this using the CD function on our calculators. So I'm just going to use the number line at the top to help us. So we want the probability that x is equal to 5. If we want to use the CD function, if at first we consider the probability that x is less than or equal to 5, so this will find us all of the individual probabilities up to and including 5. Then because we want 5 on its own, if we take off the probability that x is less than or equal to 4, so if we use our CD function again, but this time with a value of 4, then we will be left with 5 on its own, so we can find the probability that x is equal to 5 this way using the CD function on our calculators. If you haven't already tried that, please do, and you should get the same answer as you did earlier. So part B asks us to find the probability that x is greater than or equal to 4 but less than or equal to 12. So I've just highlighted that region again on our number line. So again, we'd be looking at the using the binomial CD function in this example. So to start off with, we need to consider the probability that x is less than or equal to 12. So remember, when we're using the CD function, it will give us the sum of all of the individual probabilities up to and including our given value of x, which is 12 in this case. So we get all of those. We then need to take away from that the probability that x is less than or equal to 3, and that's because if we look at our number line, we've clearly included the probability that x is 1, 2 and 3, and neither of those satisfy our condition. So once we've taken that away from our probability that x is less than or equal to 12, we should be left with 0.963. So finally, part C asks us to find the probability that x is greater than 8. So again, we need to look to use the binomial CD function on our calculators. Because we know that the CD function gives us the probability that x is less than or equal to a given value of x, we just need to consider how we can find the probability that x is greater than 8. So here we can use that the sum of the probabilities all add up to 1. And because we want every value greater than 8, so in this case we want 9 and above, this does continue past 12, so apologies, I just couldn't fit it on the screen. We can take away from 1 the probability that x is less than or equal to 8, and we're doing less than or equal to 8 because we don't have a strict inequality here, so we don't want to include 8 in our condition. So once you've done that, you should get a final answer of 0.404. Example 6.3.4. So here we have been given a scenario. Unlike the previous examples, our distribution hasn't been defined. So please can everybody start their solution by stating the distribution that they will be using. If everybody could now pause the video and attempt this example. Hopefully everybody has now attempted this question. So when a gymnast performs a routine, the probability that she does so flawlessly is 0.65. Find the probability that if she performs the routine 10 times, she will do so flawlessly on 7 occasions and at most 6 occasions. So here we are looking to model this scenario by the binomial distribution. If you haven't already considered how this meets the 4 required conditions of BINS, please can you briefly pause the video to do so. So to begin, we're going to let our random variable x, say, be the number of flawless routines. So x follows a binomial distribution where n is 10, because we know that she's performing 10 routines, and the probability that she does so flawlessly, so the probability of success, is 0.65. So we can then use this to help us find our 2 probabilities. So part I asks us to find the probability that she will perform the routine flawlessly on exactly 7 occasions. So we can write that as the probability that x is equal to 7. Because we're looking at exactly equal to, we can use the binomial PD function on our calculator. We know the value of n because we defined it in our distribution. Similarly, we've got our value for p. And then in this case, we've got x is equal to 7. So when you pop those values into your calculator, you should get 0.2522. It is also just worth mentioning that we can find the probability that x is exactly equal to 7 using the CD function on our calculators, but to do so we would have to find the probability that x was less than or equal to 7 and take off that the probability that x was less than or equal to 6. So if you want to try that, you should get the same answer as we found for part I. So then part II asks us to find the probability that she performs the routine flawlessly on at most 6 occasions. At most does suggest that we want to include 6, so we want the probability that x is less than or equal to 6. Because we're looking at less than or equal to, we know that we can use the binomial CD function on our calculators. Again, we know that n is 10, p is 0.65, and in this case x is 6. So again, once you've popped those into your calculator, you should get a probability of 0.4862. Please can everybody pause the video and attempt the exam style question included in example 6.3.5. Please just remember to start your solution by defining your random variable and stating your distribution. Okay, so I hope everybody has now attempted this question. As mentioned to begin, we need to define our random variable and state the distribution that we are going to be using. Here we are given that a spinner is such that the probability of landing on a red is 0.3. So we're going to let our random variable x, say, be the number of reds obtained, and just a tiny bit on notation, just make sure your random variable, so x in this case, is denoted by a capital letter. So looking to now define our distribution, a binomial distribution is suitable in this example. We can double check this by running through the 4 conditions, or our acronym that we've introduced this lesson, BINS. So firstly, the number of trials is fixed. Here we are told that Jane has 12 spins, so n is equal to 12. Our events are independent, as the first spin has no influence over the second, the third, the fourth, etc. We do have 2 possible outcomes for this experiment, so success would be us landing on a red, and therefore failure is us not landing on a red. Then finally, we also have a fixed probability of success, as we are told that the probability of landing on a red is 0.3, so p is equal to 0.3. So putting all that together then, we have x follows a binomial distribution of 12 and 0.3, where 12 is our number of trials and p is our probability of success, or landing on a red in this case. Again, just a tiny bit of notation, so this squiggly line here is tilde. So now we have defined our distribution, we can use it to help us calculate our probabilities in part A and part B. So first we have the probability of no more than 2 reds. So no more than implies that 2 is included. So here we can write this as the probability that x is less than or equal to 2. So just remember that we did let our random variable x be the number of reds obtained. So from here we can use the binomial CD function on our calculators, and once we've used that we should find our probability is 0.253 to 3 significant figures. In terms of the actual values that you're looking to put in your calculator for this example, we have n is 12, so that's our number of trials, our probability of success, so in this case landing on a red is 0.3, and then x is 2 in this case. Moving on then, we're asked to find the probability of at least 5, so again 5 is included, but we want the probability that x is greater than or equal to 5. Now remember that the cumulative distribution function always considers the probability that your random variable is less than or equal to any possible value of x that we defined. So we do need to rewrite the probability that x is greater than or equal to 5 if we want to use our CD function on our calculators. As we know, the sum of the probabilities for all outcomes of an event equal 1. The probability that x is greater than or equal to 5 is the same as 1 minus the probability that x is less than or equal to 4. So again, at this point we can use binomial CD on our calculators. And exactly the same as in part A, we have n is 12, p is 0.3, but in this example we have x is equal to 4. So then once you've found that probability, if you take it away from 1, you should be left with 0.276. Just a tiny note here, whenever you're using the cumulative distribution or you're finding any values using your calculator, don't round too soon because it can affect your final answer. So finally, in part C, we are told that Jane is using the spinner for a class competition and she wants the probability of winning a prize to be less than 0.05. The distribution has remained the same because each member of the class will have 12 spins. We therefore need to find the value for x such that the probability that our random variable is greater than or equal to this given value is less than 0.05. So there are a couple of ways that you can do this, so if you haven't done it the same way as me, that's fine. I've used trial and error for this example. So first I've considered the probability of landing on 6 or more reds. Because I want to make use of the cumulative distribution, I've taken 1 minus the probability that x is less than or equal to 5, and that gives me a probability of 0.1178. Because that is greater than 0.05, we haven't yet met Jane's condition to win. So next I've looked at the probability of landing on 7 or more reds, and this comes out at 0.0386, which is less than Jane's condition, and therefore we can conclude that the number of reds needed to win is 7. Just a thought that I want to leave with you all. If you have done it this way, that's perfectly fine, but just something to maybe look at and consider, as trial and error can be time consuming sometimes. Is there a way that you could use your tables to find this value of 7?